All right, well, happy Friday, and we'll get started. We are continuing on talking about floating point numbers. So on Monday, we started talking about floating point numbers, and just we have to keep in mind that on the computer, floating point numbers do not have the same behaviors as real numbers. So things like, the order of operations between like whether you multiply or divide first, that makes a difference. 10 times 3 divided by 3 is 10, but 10 divided by 3 times 3 is not equal to 10. You get 9.999, right? And 0.1 plus 0.2 doesn't equal 0.3 on the computer because of floating point numbers. I introduced the IEEE 754 floating point specification. This is how our computers store numbers. This is done at the hardware level, and it's done pretty much on all computers today. I suppose somebody could come up with their own computer system that doesn't use this system, but it would not be supported. But pretty much every single computer that you can buy, your laptop, your phone, whatever it might be, is going to follow this numeric specification. And again, it's implemented at the hardware level. So whether you're using R or Python or any kind of software, it's not going to affect how it stores numbers. The numbers are going to be handled the same way. The primary numeric type that we use in R is the double precision floating point number, and that means it uses 64 bits to store the number, 1 bit for the sign, 0 or 1, 0 if it's positive, 1 if it's negative, 11 bits for the exponent. 11 bits means you can store 2048 unique values. Of those, 2 of them are designated for special cases. All zeros and all ones are special cases. The remaining 2046 represent positive and negative integers, anywhere from negative 1022 to positive 1023. And then the remaining 52 bits are used for the mantissa, which is used to kind of store our number in binary scientific notation. Okay, to kind of explore and understand how the IEEE 754 system works, we're going to explore with a miniature version of this where I only have 8 bits, and I will designate 1 bit for the sign, 3 bits for the exponent, and 4 bits for the mantissa. And so this is very, very similar. It's just that I can only represent, far fewer values, okay? So 1 bit for the sign, so still 0 if it's positive, 1 if it's negative. 3 bits for the exponent means I have 8 unique values, 2 to the third, 8 unique values that I can represent. 2 of them will be special cases. That leaves 6 remaining, and so we'll represent the numbers -2 to +3. That's the 6 unique values that I can represent with the exponent. And then the remaining 4 bits will be used to express the mantissa. So this is what we have. So these are our 8 unique values that we can represent with 3 binary digits. Okay, from 000 to 111. Again, all zeros is a special case, and all ones is a special case. The remaining 6 are used to represent positive and negative values. So we go from -2, -1, 0, 1, 2, 3. So those are our 6 unique values. And then the last 4 bits are for the mantissa. Okay? And in binary scientific notation, the digit in front of the dot will always be a 1 because it can't be a 0. And so I think we had an example. Here's another example. Do you guys want to try to work through this? let's see if we can figure out what the exponent is. So what is this exponent? So in binary it's 2. How much of a bias do we have? It's going to be -1. Okay, so this exponent 0, 1, 0 will represent -1. So in binary 0, 1, 0 is 2. We apply the bias of -3, and so our exponent value is -1. Okay, and then our mantissa bits are 1, 0, 1, 0. So we're going to have 1.1010. So 0.1 is a half, no quarters, and 1/8. So 1/2 plus 1/8 is basically what, 5/8. So I've got 1 and 5/8 multiplied by 2 to the -1. So 1 and 5/8 divided by 2, or a half of that. So what is that? That's going to be 1/2 plus 5/16. I don't know how to do that. Okay, some number. So 1 and 5/8 divided by 2. I need a I need a calculator. So 1.625 divided by 2, 0.8125. 13/16 is going to be our value here. Okay, so negative. So yeah, here we go. Sign bit is 1. The value is going to be negative. Exponent is 0, 1, 0. Exponent in binary is 2. The bias is 3, so the exponent is -1. The mantissa bits are 1, 0, 1, 0 with the leading 1. That's going to be 1.1010. So I have -1.1010 times 2 to the -1. So this is, 1 plus 1/2 plus 1/8, 5/8, or 1 and 5/8 times 1/2. So this gives me, -13/8, -13/16, 0.8125, -0.8125. Okay, so this is how our floating point numbers work. Another way we could do this is, instead of doing 1 and 5/8 times 1/2, you could also take this, roll the binary point over to the left one, and so now I have 0.11010. So that would be 1/2, 1/4, and 1/16, and that gives us the same value of 13/16 negative. Okay, we run into an issue, however. Okay, if we have this all zeros, this should probably represent the number 0. Okay. However, with our current way we've specified floating point numbers, this would represent 1/8. Okay, so with our current system, we have the sign bit is 0, the exponent bits are all 0, and the mantissa bits are all 0. Okay, with the bias, the exponent would be 0 minus 3, -3. The mantissa bits are all 0, and so with the leading 1, okay, this is the problem. We said we always assume the leading digit, the digit in front of the binary point, is always going to be a 1. And if that's the case, we can never have a 0, right? If we always have a 1 here, we'll never be able to represent the number 0. And so that causes conflict. So you might say, well, why do we always have to represent with a 1? Well, in almost every other number, every number other than 0, you could have a leading bit. You'll have a leading bit that's not 1, okay? And it's only in 0 that you don't have something that would be something other than 0. So it feels kind of silly to just have this 1 bit designated to say, is it 0 or not 0? So we're not going to do that. So instead, we have what we call denormalized mode. So remember I said when the exponent bits are all 0, it's a special case. We have 2 special cases for the exponent bits. It's when we have all 0s in the exponent and when we have all 1s in the exponent. So when we have all 0s in the exponent, we have we're going to be in denormalized mode. So I wrote, it was useful for us to assume that in normalized binary scientific notation, there's always going to be a leading 1 in front of the mantissa bits, and this reduces redundancy because we're not going to need to waste one of our mantissa bits to say something that's going to kind of be 1 all the time anyway. Okay, but it does lead to the problem is that if the binary digit in front of the binary point is always a 1, we have no way to represent the value 0. So we have denormalized mode. When the exponent bits are all zeros, then the digit in front of the mantissa bits will be a 0. So the leading digit is going to be 0. However, if you just continue to apply the rules as they are listed, you end up with a kind of a like a gap in the number line. And so to kind of avoid that discontinuity or to avoid that gap, in denormalized mode, the exponent bias is 1 less than usual. So in our miniature floating point system, our bias is normally a 3. When we're in denormalized mode, it's going to be a 2. In double precision floating point, normally your bias is 1023. When you're in denormalized mode, it's 1 less than that. It's going to be 1022. So when we apply that, when you have all zeros, okay, your exponent bits are going to be all 0. So that means we're in denormalized mode. Our bias term is going to be 1 less than usual. We have a bias of bias of 2, so the exponent is going to be 0 minus 2. We get an exponent of negative 2. Mantissa bits are all 0. In denormalized mode, the leading digit is 0, so I get 0.0000 times 2 to the negative 2, and that's going to be 0. So having all zeros in the in your floating point number represents the number 0. This is not very exciting, but we have that. Okay. All right. Let me go ahead and give you your first view quiz answer. Today's first view quiz answer, week 6 Friday, is the letter A. A as in apple. Okay, the other special case is when we have all ones. All ones in the exponent gives it a special meaning. So if you have all ones and you have in the exponent sorry. When you have all ones in the exponent and all zeros in the mantissa, that represents infinity. Okay, so it's not actually, it just represents mathematically on the computer this concept of infinity. Of course, it's not actually infinity, but mathematically or on the computer we have this representation for infinity, and we have a positive infinity and we have a negative infinity. Okay, and that's, you have all ones in the exponent and all zeros in the mantissa. If you have all ones in the exponent and something other than all zeros, then you get nan, not a number. So nan just is used to represent things that are not numbers. In R, there's a distinct value for missing and a distinct value for nan. Okay, nan is going to be the result of, I think if you try doing 0 divided by 0 in R, you get nan. If you do like infinity minus infinity, you also get nan. Just kind of these things that are not numbers. So let me just try 0. 0 divided by 0 gives us nan. Okay, that is different from NA. Okay, so I can do type of for here, okay, wait, let me say x is 0 over 0. So this is this, and if I say type of x, that is double. All right, if I say y is NA, what is type of y? The default is going to be, it's going to be type logical. I could create z, a combination of x and y. Okay, and so here I have nan and NA. The second value here, though, if I ask what is the type of on this, what is the type of on Z2? is going to be double, okay? This NA, Z2, is an NA, but it's a double NA because because vectors all have to be of the same type, right? So this NA is a logical NA, this NA is a double NA. We have distinct NA and NaN are different in R. In say Python, however, if you're using pandas, NaN is used to represent missing values. But anyway, NaN is not a number, okay? All right, this is the smallest non-zero value that we can represent in our floating point system. What is this number? Smallest non-zero value we can represent. So this is all zeros in the exponent, and then our mantissa bits are 0, 0, 0, 1, okay? So this means we're in denormalized mode. Our bias is 1 less than usual, so we have a bias of 2. The exponent is -2. Mantissa bits are 0, 0, 0, 1. Our leading digit is 0. So I have 0.0001 times 2 to the -2. So 1 place after the point is a half. 2 places after is a quarter. This is an eighth. This is a 16th. So I have 1/16 times 2 to the -2. So this is equal to 1/64. Okay? I have 1/16 times 2 to the -2. 1/64. 0.015625. This is the smallest number I can represent in my floating point system. Okay, what is the next smallest value I can represent? Okay, so I started off with 0, 0, 0, 1. Now this is the next smallest number, 1, 0. So again, now we're still in denormalized mode. Exponent bits are all 0. Bias is -2. Denormalized mode, I got 0, 0, 1, 0. So this is 1/8 times 2 to the -2. Okay, 1/8 times 1/4 is 1/32. This is basically 2/64. Okay, so the previous number was 1/64, and now I have 2/64. So I've taken a small step, and the increment from the previous value to this value is 1/64. I went from 1/64 to 2/64. Okay, what's the next number? The next number, this would be 3/64. Then we have 4/64, 5/64, 6/64, so on and so forth. Our increment between values is still 1/64 at a time. Okay, I can keep going, and we will reach up, and we will get 1, 1, 1, 1. This is the largest denormalized value. I have all zeros in the exponent. I have 1, 1, 1, 1 in the mantissa. So this is my number in denormalized mode, 0.1111 times 2 to the -2. 0.1111 is 15/16, okay? And I have times 2 to the -2, so this is 15/64. So kind of counting, we start at 1/64, 2/64, 3/64, 4/64, 5, 6, 7, 8, 9, 10, all the way up to 15/64. Okay. Now this number, so kind of counting in binary, the next thing that's going to happen is this is going to become a 1, and these all become zeros. Okay. And now we are in normalized mode, and this is the smallest normalized value I can represent. So our exponent is 0, 0, 1. We have a regular bias. A bias is 3. The exponent is -2. I'm not in denormalized mode, so rather than having a bias of 2, I have my usual bias of 3. So my exponent is 2 to the -2. Okay. The mantissa bits are all 0, and the leading digit is a 1. This is per normal, so this is going to be 1.0 times 2 to the -2. This is equal to 1/4, or 16/64. So we went from 15/64 to 16/64, or 1/4. Okay. What's the next value going to be? The next value, this last bit, is going to change to a 1. Okay. And what number is this? Okay. So our bias is 3. Our exponent is -2. So I have 2 to the -2. This is 1.0001 times 2 to the -2. So this is 1 and 1/16 times 1/4, and so this gives us 17/64. Okay, and so so we went from 16/64 to 17/64. Okay, I mean we could say 1/4, but I'm doing over 64 to kind of just give you that we're just kind of counting up by 64ths. Okay, so this is 17/64, and we would keep going, and we would get 18/64, 19/64, 20/64, 21/64, 22/64, and we keep incrementing by 16/64 until this all fills out with ones. And what number is that? If I have 0, 0, 0, 1, and then this becomes all ones, can we figure out what number that is? 0, 0, 0, 1 for our exponent. This all fills out to ones. And so this is 1 and 15/16 times 2 to the negative 2. So what, 16/16 plus 15/16, I'm at 31/16 times 1/4, so I'm at up to 31/64. Does that feel okay? 31/64. All right, and then what happens next? What are we going to get next? So if I increment, if I add a 1 to this in binary, so what is this in binary? 1 plus 2 plus 4 plus 8 plus 16, that's 31, okay? So this is, we're at 31, we're at 31/64. So if I add 1, we're going to be at 32, okay? And so this is our next value as we increment. So what is this? So now we have 0, 1, 0 for our exponent. This represents the number 2. Okay, how much is our bias? Our bias is 3. So our exponent is 2 minus 3. We have an exponent of -1. 2 to the -1. My manticipants are all 0 here. 0, 0, 0, 0. So the manticipants are we're going to have 1.0000, so that's just 1, times 2 to the -1 for my exponent. -1 for my exponent. So 1 times 2 to the -1. So that's just 1/2. Okay, 1/2 is now 32/64. 32/64. Okay. Okay, what do you think the next number is going to be? What's been the pattern so far? So we went from 18/64, 19/64, 20/64, 21, 22/64. We get up to 31/64, and then we're at 32/64. Okay, so what do you think the next number is going to be? So we would feel like, okay, the next number is going to be 33/64. That's what it feels like. Okay, but this is the genius of floating point methods, is that the next number is not going to be 33/64. Okay, it's going to be 34/64. Okay, so why? All right, well, let's take a look. Okay, so we are now at our exponent is still 0, 1, 0, so we still have an exponent of -1, right? 0, 1, 0 represents 2, bias of 3, so our exponent is still -1. The leading digit is a 1, and our manticipants are 0, 0, 0, 1. So I have 1.0001, so that's 1 and 1/16 times 2 to the -1, or times 1/2, and this is going to be 17/32, and that is 34/64. Okay, so we jump from 32/64 to 34/64. We are at 17/32. Okay, and what's the next thing going to be? Okay, it'll be 1 plus 2/16 times 2 to the negative 2. 1 plus 2 sixteenths would be 18 sixteenths times 1/2. We're going to be at 18 30-seconds. Okay, so the next number, if I roll it over, I've got 1 plus 1/8 times 2 to the negative 2. This becomes 18 over 32, right? So we go from 17 30-seconds up to 18 30-seconds, okay? And if we keep going, we'll get 19 over 32, 20 over 32, 21 over 32, 22. Okay, so now we are counting up by 30 seconds. So our step size has kind of doubled from 60/4 now to 30 seconds. Okay, and we keep going until we reach our mantissa bits being all 1. I get 1 plus 1, 1, 1, 1, 1, and this is going to be 31 over 32, 31 30-seconds. Okay. So in the beginning, we started off with increments of 1/64 at a time. And as our numbers get bigger, now we increment by 30 seconds. Okay? And so I go all the way up to 31 over 32, 31 30-seconds. And then so the next thing, after I have all 1s in the mantissa, this is going to roll over, and this is going to change to a 1. So my exponent becomes 0, 1, 1. And now I have all 0s in the mantissa. So my exponent is 0, 1, 1. My exponent 0, 1, 1 is 3 in binary. With a bias of 3, that becomes 0. So this is my exponent value is 0, 2 to the 0, basically 1. The mantissa bits is all 0. Leading digit is 1. So I've got 1.0 times 2 to the 0 times 1, which is basically just 1. This is how we represent the number 1 in our miniature floating point. And so that's 32 30-seconds, 32 over 32. So I've gone from 31 over 32, now we're at 32 over 32. Okay, what's the next number going to be? So we're at 1. And if I increment my bit, the last bit, to a 1, so can we see we're going to get 0, 0, 1, 1, and then on the next slide we'll have 0, 0, 0, and then it's just going to be this one last bit. This is going to change to a 1. So what number is that going to be? We will add a 16th. So our step size goes from 60/4 to 30 seconds, and now that we've reached 1, our step size is going to be 1/16. So the next number is going to be 1 and 1/16, or 17 sixteenths. Okay, because let's go ahead and take a look. Our exponent is still 0. We're at 2 to the 0. My mantissa bits are now 0, 0, 0, 1. So I've got 1.0001. So this is 1 and 1/16. Okay, times 2 to the 0, or 1. And so this is 17 sixteenths. So the increment between values is 1/16. The next number will be 18 sixteenths, then 19 sixteenths, and we'll kind of keep going until we reach 31 sixteenths. Right? So this is 1. So we just kind of keep counting up until we get to 31 sixteenths. And then the next number would be 32 sixteenths, or 2. Okay? So then we get 2 16/8. And now that my exponent is 100, okay, with my bias, so this is 100 is 4, okay, with a bias of 3, I'm multiplying my mantissa times 2 to the 1, right? So basically I have 1.0000 times 2 to the 1, so that's 2. And now I have 1.0001, so that's 1 and 1/16 times 2. So I get 17 over 8. And then we get 18/8, 19/8. And we keep going until we get to 31/8. Our step size is now 1/8. Is that okay? So right here we're incrementing by 16ths. Now we increment by 8ths. So I get basically 16/8, 17/8, 18/8, 19/8, up to 31/8. And then the next value my exponent is 101, 5. With a bias of 3, we get 2 to the 2, exponent value of 2. So this represents the number 4. And now my increments are 1/4. So we go from 16/4, 17/4, 18/4, 19/4, all the way up to 31/4. Okay. I created a kind of this little floating point worksheet or a little handout. That kind of shows all of these things. So we start off at all zeros. This is denormalized. So it's 0.000 times 2 to the negative 2. Okay. This is 1/16 times 1/4, 1/8 times 1/4, 3/16 times 1/4, so we're at 3/64. We get up to 15/64, then 16/64 or 1/4, and we kind of keep going, 17, 18, all the way up to 31/64. And at this point, we get to 1/2, and then we get to 17/32, 18/32. Our step size is 1/32. We get up to here until we get to 1. And then we keep going. Step size is now 1/16. We go 17/16, 18 up to 31/16. At 2 until we get to 31/8. Okay. And then over here we're at 4th, and our step size is 1/4. Okay, which is I think where we are here. Our step size is 1/4. And this kind of keeps going until we reach here, which is now, so we get to 31/4. So what's that? 7 and 3/4. Okay, 31/4. And then we get to 8. And now our step size is 1/2. So we go from 16/2, 17/2, 18/2. And we get all the way up to 31/2. 31/2 is 15.5. This is the largest finite number I can represent in my floating point system. Okay, the very biggest number I can represent is 15.5, which seems kind of silly. I can't represent the number 16. That would blow up my system. Okay, as soon as I increment the next thing, now I have all 1s in my exponent, all 0s in my mantissa, and this represents infinity. Okay. So I count by, I go 1/64, 2/64, 3/64 until I get to basically 32/64, 1/2. Then I count by 16ths, 33/16, 4/16, okay? Or I'm sorry, 17/16, 18/16, until we get to 31/16, or 32/16, so 2, and we keep going. And then, but anyway, the largest number I can represent is 31/2, 15.5, and then after that, the next number becomes infinity. Okay, so my increment between values is 1/2. The largest, this is the largest value I get before infinity, and this is all kind of detailed out here. This is what our number line looks like. Starting at 0, our step size is 1/64. As our numbers get bigger, our step size increases, okay? Our step sizes become 1/32, then our step sizes become 1/16, then our step sizes become 1/8, then our step sizes become 1/4, okay? Going from, we get 2.125, 2.25 up to here, okay? Then we get our step size is 1/4, 4.25, all the way up to what, 7.758. Then our step size is 1/2. And we go from 8, 8.5, 9, 9.5 up to 15, 15.5, and then after that, we reach infinity. Okay. So that's kind of the neat thing about floating point numbers is that as your numbers get bigger, your step size also increases. Okay. So let's look at kind of the specifics for double precision floating point. What happens here? Okay. What is the smallest possible number I can represent in double precision floating point? The smallest possible number I can represent is going to be all zeros in the exponent. Okay, so we're going to be in denormalized mode. All zeros. Our bias is 1 less than normal, so my bias is going to be negative 1022. Normally our bias is 1023, but I'm going to do 0 minus 1022. So I've got 2 to the negative 1022. Okay, the mantissa bits will be, I've got 52 mantissa bits, so I'm going to have all zeros and then a 1. Okay, all zeros and then a 1. So that represents 0.000001, so that's going to be 2 to the negative 52. Okay, so basically I have 2 to the negative 52 over here times my exponent of 2 to the negative 1022. And so this is going to be 2 to the negative 1074. 2 to the negative 1074. This is the smallest possible number I can represent on a computer with double precision floating point. And so I can type in, into R, you can type in 2 to the negative 1074, and you will get a number. 4.95 times 10 to the negative 324. Okay, this is the smallest possible number. So it's a pretty small number. It's like 0.000000, 323 zeros, and then a 494, so on and so forth. Okay, and then if you ask for anything smaller than this, if you try 2 to the negative 1075, okay, or if you take this number, so I can say A is going to be 2 to the negative 1074, right? So what is A? Here's that. If I try doing anything with this, A divided by 2, I get 0. The computer cannot, it is physically incapable of representing a number smaller than this using double precision floating point. Okay, we just don't have any more bits. Okay, so we can't try to do 2 to the negative 1075. That gives us 0. Okay, what is the smallest normalized number? Okay, the smallest normalized number will be, our exponent will be all zeros with a 1. Okay, the exponent is going to be 1 minus 1023, negative 1022, 2 to the negative 1022. My mantissa will be all zeros, so I'm going to have 1.0, 0000, so basically 1 times 2 to the negative 1022. So that is the smallest normalized value I can represent. So that's 2 to the negative 1022. This is my smallest normalized value. This is known as double X-min. Okay, this is these are properties. If you type in double.machine $double X-min, this is the exact same number. It is the smallest normalized number your computer can represent. Okay, it is not the smallest number it can represent, because again, the smallest number it can represent is 2 to the negative 1074, right? Which is 2 to the negative 52, smaller. Okay, but this is the smallest normalized value. What is the second smallest normalized value I can do? Okay, basically I have the same exponent. And I can do 2 to the negative 1022, and my mantissa is going to be all zeros except the last bit is going to be a 1. So basically I can do 1 plus 2 to the negative 52, and I get two different numbers. These are distinct values. X is 2 to the negative 1022, Y is 1 plus 2 to the negative 52, plus times 2 to the negative 1022. And these are distinct values. Okay. If you show more digits, you can see this last digit is a 014, and then here I got 019. These are distinct values. X is not equal to Y. Basically, the smallest value that you can add to increment one number from the next, the smallest value you can add to 1, where the computer recognizes it as a number other than 1, that is known as machine epsilon. Okay? What is the smallest value you can add to the number 1 and have it be a distinct value from 1? Because I have 52 bits in the mantissa, that smallest value is going to be 2 to the negative 52. On my miniature floating point, what is my machine epsilon? if I have 4 bits in the mantissa, the smallest value I could add to 1 and have it be distinct from 1 is 1/16. So I could go from 1 to 17/16. The smallest value I could add was 1/16. So here, because I've got 52 bits in the mantissa, the smallest number I can add is 2 to the negative 52. And that's machine epsilon. And so you can ask dot machine double dot epsilon, and you get 2 to the negative 52, same value here. And so I can do 1 plus 2 to the negative 52, and we would have 1 versus 1.0002. Your normal, if I say B is 1, and D is going to be B plus 2 to the negative 52. Here's B, here's D. B and D look very like the same, but if you ask, is B equal to D? They are not, because D is B plus machine epsilon. Okay, you have to ask for digits options. If I do options, digits equal 20 or something like that. Okay, here's B, here's D, and we can see, okay, these two things aren't exactly the same. If you try to add anything smaller than machine epsilon, if you try to do 1 plus 2 to the negative 53, the computer is not able to distinguish the two. Okay, so if I have A is 1 and B is going to be 1 plus 2 to the negative 53, and I ask, what is A and B equal to each other? That's going to be true. Okay, so again, here's B. B is exactly 1. I'm going to say E is going to be B plus 2 to the negative 53. 2 to the negative 53. So what is E? E is still 1. Is B equal to E? That's true. Okay, remember D is 1 plus 2 to the negative 52. B and D are not equal, but B and E are equal. I can't add 2 to the negative 53 to 1. Okay? Even though the computer is able to represent 2 to the negative 53, you cannot do this plus 1. Okay? Because if you try to do that plus 1, it's just 1. Right? It's trying to add in our floating point here, if I have the number 1 and I say add 1/32 to it, we can't represent 1/32, 1 and 1/32. And with the number of digits I have, I can't represent 1 and 1/32. In IEEE 754 double precision floating point, this is the number 1. We have our exponent bias is negative 1023, so basically I represent 1023 in my exponent, which is 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, and then all zeros in the mantissa. This represents the number 1. Okay, and then this is 1 plus machine epsilon. Okay, so this is now 1, all zeros, with the very last bit being a 1. And so this is 1 plus 2 to the negative 52. And so you can see why I'm not able to add anything smaller than 2 to the negative 52 here. Because this is, over here is the number 1. The smallest thing I can add is changing this last bit to a 1. Okay? If I change that last bit to a 1, that's 1 plus 2 to the negative 52. I don't have any more digits to add anything smaller, like 2 to the negative 53. So this is the smallest thing I can add. So that's machine epsilon. Okay, here's a thought experiment. Let's say you ran this loop. You start off with x equal to 0, and you say x is x plus 1. So you're just going to start at 0. You go 1, 2, 3, 4, 5, and you just say while true. It's an infinite loop. Let's say you leave for a year and you come back to your computer. Okay, and it's been counting really, really, really fast. And it's been counting, I don't know, you come back a decade later. What is x going to be equal to? Will we have reached infinity? Will we have reached, will it get to a number? What do you think?
I don't know if the top but it's stuck at the point that like the step size is like 2.
That's exactly where it gets stuck, okay? So as we keep counting, our step sizes get bigger, right? We start off at 1/64th, then 1/32nd, then 1/16th. Same kind of thing. We start off with step sizes of negative 2 to the negative 52, 2 to the negative 51, 2 to the whatever. We reach a point where our step size becomes 1, and then we reach a point where our step size becomes 2. It gets stuck when the step sizes get up to 2. So it's not gonna reach infinity or machine double X max. It gets stuck at 2 to the 53. And let me just show you, okay? So here is, you can do x, x is this number, okay? And then I can do x plus 1, and then let me just do this. X is gonna be x plus 1, and then I'm gonna print x. Okay, so I can add 1, and then you can see this last digit goes up to 991. I add 1, I get 992, and then I get stuck at 992. Because we're at a point, if I say, what is 2 to the 53? This is that number. And at 2 to the 53, the smallest thing I can add is a 2. So I could do 2 to the 53 plus 2, and I can go on. So if I did x plus 2, then I can keep going. Okay? But if I try to do any of these things with x plus 1, okay, then it gets stuck, okay? All right. So once you get to this point, adding 1 no longer changes x, okay? But you can add 2, right? And so, and that's because our step sizes has gotten to the size of 2. So we can't add 1 anymore, we have to add 2. And then, and so it feels weird, right? Running an infinite loop doesn't lead to reaching infinity or the largest possible number you can represent, but it gets stuck at this finite number, 2 to the 53. And at that point, your step sizes has gotten to be 2, and so you can't get anything bigger. Okay, this is the largest possible number we can represent on the computer. Okay, it's all 1s and a 0 on the exponent, so that has an exponent of 1023, and then my manticipits is all 1s. Okay, so that's 1 plus 2 to the minus 1 plus 2 to the minus 2 to 2 to the minus 3, so on and so forth. Okay, and if you do that sum, you get 1.797 times 10 to the 308. This is the largest possible value. This is also known as double X max, machine double X max. So A and B are equal to each other. If you try to add anything to this, okay? If I try to add something, at this point, our step size is now 2 to the 970, a very big step size, okay? If I try to add 2 to the 970 to this number, we reach infinity, okay? So at this point, A is equal to double X max. If I try to add 2 to the 969, 2 to the 969 is a really big number, but my step size is even bigger, okay? If I try to add this number to this number, it can't distinguish. Here's A, here's X. It says, is A and X are the same, right? If you say, hey, add 200 to the 969, are you gonna get a different number? According to the computer, it's the same number. A and X are the same, okay? But if you try to add 2 to the 970 to this, it explodes, and the computer says, now you are at infinity, okay? So that's the largest possible thing. So what do we do? Okay, let me give you your last view quiz answer. Last view quiz answer is the letter D. D is the last view quiz answer. And so what do we do? Okay, to handle this, we can do all equal. Yeah. Oh, did I? Oh, okay. Sorry, second answer is C. Okay. All right, I'll just give you all three. A, C, D. Okay. A, C, D. Thanks for sticking around. Thanks for coming to class today. So, 0.1 plus 0.2 doesn't equal 3. So what you can do is you can do something called all equal. 0.1 plus 0.2 versus b. All dot equal is like, are they approximately equal? Are they approximately equal? That means sometimes things that aren't actually equal will come back as they are approximately equal. So if you actually wanted to store in your calculator 9.99999, and that was the actual value you wanted, right? Sometimes you might actually want, I don't know, discounted price, 9.99999. And then you say, is that equal to 10? This function is going to say, yeah, those are equal to 10. But you know, that might not be what you actually wanted, okay? So anyway, you know, are A and B equal? They're false. Are they approximately equal? That comes back true, okay? So you have a little bit. There's something known as catastrophic cancellation. You can read about this on the notes, but I just wanted to kind of go over floating point numbers, just kind of some of the implications. And so the largest number we can represent is on the order of 10 to the 308, which is a big number, but it's not infinity. And anything after that, the computer will say it's infinity. Okay, we will end here for today. Have a great weekend. Enjoy your Monday off, and we'll see you on Wednesday.